In this lecture, the third part in our closer examination of earthly storms, we'll take a look at tropical air disturbances and how they factor into the development of some of the largest storms on our planet today. Let's begin by looking at probably the most well-known tropical air disturbance north of the equator, and a tropical air disturbance is very much associated with North America and the Gulf of Mexico. This is known as the easterly wave. The easterly wave is a weak tropical air disturbance that moves as a pressure trough. It's a trough of low pressure that moves through the Caribbean and what is historically the French West Indies. It's considered to be weak in terms of its storm front effects. However, it is an early predictor for the tropical disturbance patterns of the hurricane season, which generally will follow later. Storm disturbances of this kind generally will move from the southeast to the northwest. And again, this easterly wave, and you can see the isolines or the isobars and how they refract around this particular front. These, in a sense, are going to be important pressure predictors for the development of these storms. Winds will converge on what becomes a very large low-pressure cell, and that, of course, as you know, results in air uplift and some of that convection storm activity, which we see throughout generally the summer months, but then also what we see indirectly during some of our cooler seasons. Let's take a closer look at a hurricane, and let's look at it almost as if we're putting together a recipe for a storm. A hurricane, by definition, is a severe storm. It's geographically the largest of all storm bodies. We, again, closely associate the development of hurricanes in our modern age, or in the Holocene epoch, to be directly relatable to the nature and movement of low depression or low pressure troughs in this case, and atmospheric depressions such as the easterly wave. The term hurricane is synonymous with the term typhoon, a mid-latitude cyclonic storm that brings very heavy rain and constant winds that in this case extend, or exceed rather, 100 miles per hour. Commonly, a tropical storm such as a typhoon or a hurricane will, in a sense, have a diameter which will exceed averages of 100 to 500 miles. In this schematic diagram, if you look along the base of the diagram, you'll see kilometers. At the top of the diagram, you will see an estimate in miles. And again, that's what we are looking for. We're looking for a convection storm body that is really large in the amount of geographic space that it's covering. What you'll also see is that generally it will be resting on top of or covering warm ocean waters. Warm ocean currents can be tracked on this image to give you an idea of where generally they will localize. A couple things going on here when you look at it. First and foremost, you will notice that the warm water currents generally will be localized to deep and shallow ocean currents that will eventually run parallel to the Earth's equator. Now again, when we see these ocean currents upwelling, rising closer to the surface as they're being warmed, and then almost turning in a 90-degree angular fashion, we're really seeing what is the Coriolis effect. Variations in that 90-degree twist or turn, whether it's to the right or to the left or to east or to the west, depending on the hemisphere that you're in, generally will be confounded by other factors that tie into not only airflow, but also the flow of water molecules on the planet. So this would be things like friction, for example, or local pressure gradients with regard to the lower troposphere. When we are studying the development of these large convection storms, in this case hurricanes, We will turn our attention to the Gulf Stream and the Northern Pacific Equatorial Current. These will give us a sense of where these troughs form and the general direction of their movement. The Gulf Stream itself is most important in being able to track what becomes a low pressure environment. Some of the other major atmospheric disturbances that we would associate with the monsoon season or with the development of these typhoons, generally located to the east in the northern hemisphere of what we have in terms of the Gulf Stream, can be tied to the northern Indian equatorial current and the Pacific equatorial countercurrent. Now let's turn our attention back on the development of this large storm body. As a side note, I should mention your text will abbreviate wind speed as it relates to storm actions in the same manner that other courses that you have probably taken will, such as physics. They conceptualize speed, in this case, in terms of meters per second. The reason that I am talking about miles per hour is that I really want to give you something that you can relate to. We all drive cars, we all measure our own speed in terms of miles per hour. So that just kind of gives you a deep understanding of how powerful these storms are. So if I was to say 22 miles per hour, for example, or 10 meters per second, I'd be talking about the same thing. But one is easier to conceptualize than the other because of your cultural mind. So back to storms. So these storm fronts, the ones that are associated with the development of monsoons and typhoons, generally will differ from our common North American pattern, moving again west to east. They will be generally moving from east to west in most environments, at least those that are associated with the northern hemisphere. Once these low pressure cells make contact with the continental coastline, they generally will move north. So they have that additional quality of movement that we need to consider as we're looking at the basics of hurricanes. But let's look at their development. Generally, hurricanes or typhoons will develop on the western side of earthly oceans. Our Atlantic seacoast, or seaboard rather, is a prime example for this practice or this fact. Unlike some of the other fronts and related storm activities that we have looked at up to this point, these storms generally will remain close to their point of origin, even though a hurricane like Hurricane Katrina, for example, moved over 750 miles from its air and water current source. This is only a small region when we're looking at not only the overall size of an air mass, but then also the overall expanse of our earthly oceans. So scale in this case is very important. The most dramatic aspect of a hurricane visually is the cloud column, which we're seeing in cross-section once again in this diagram. Probably one of the most recognizable aspects of a hurricane from below or above is this very unique cloud structure. Let's take a look for a second now and organize this into your notes in terms of how a hurricane forms, similar to almost a recipe. This recipe is going to have 6 parts to it. So we'll begin this process and work through how this very unique engine, this natural storm engine, develops. First, you need warm water. In this case, we're looking for water that is above 75 degrees Fahrenheit. In addition to this, and again, this is this first part of the recipe, in addition to this, we also need to see that there is a warm, moist, overlaying air mass. So we need an air mass, in this case, that is probably marine and warm. We need one that is situated generally, or at least for the most part, over warm water. And then we need something that will have a pretty good measure of localized lower atmospheric water vapor. Next, or second, you need a low pressure tropical air disturbance, such as our easterly wave. and it must not dip below 8 degrees north or 8 degrees south in terms of its latitude. So that low pressure, generally tropical air disturbance is important. We need that trough that will eventually develop into a major and very powerful cyclonic low pressure air cell. Next, or third, as I said, it is a low pressure storm body. So atmospheric pressure, as this storm begins to develop, must be lowest at its center. The air is eventually caught up into what becomes a rapid air flow, cyclonic in nature, at the boundaries of a well-developed, centralized low pressure source region. It is this third characteristic that makes what appears to be some of the predictability of this developing storm body to be something that we can use to describe and discuss the hurricane season and areas of potential environmental hazard. Fourth, or the fourth characteristic that we need to have this amazing storm engine develop, the air, when it rises, it has to rise at a very rapid rate. So as it develops this cyclonic air flow around a low pressure point of origin, we eventually need to see that warm air being pushed up into higher elevations within the Earth's atmosphere. This will cause the release of the majority of the water vapor in the developing storm body. This will generally come down as heavy rain, and it will also help to develop additional aspects of that very unique, very dramatic, very large cloud column. On this diagram, as you get close to the 0 point, whether it's in miles or kilometers, you will see where the heavy rain generally will develop. However, the arrows are demonstrating that there is warm, moist air from on top of the warm ocean water being pushed up into the upper atmosphere. Generally, you would follow those arrows until you see at least a portion of the arrow symbol being then rerouted down back through the center of that column. That's what we're discussing here, what I'm describing here, when we have this warm water vapor and air vapor that is being pushed up higher into that cloud column, and then immediately, once it hits that kind of thermal cline near the top of the troposphere, then it's being dumped back down, and it's releasing all of that water vapor that's, in a sense, contained within it. Fifth, we will start to look at an area within the troposphere known as the tropopause, kind of the top of this very important section of the atmosphere that contains the majority of life on the planet, if not all of the life on the planet. So once the air reaches the tropopause, it is cooled very rapidly in such a way that it is either forced back down into the eye, as I mentioned before, and contributes that very heavy rain as it is dropping its water vapor. Or, in a sense, it is being pushed outward to create that top to the column. So, just to restate this fifth characteristic, once the air reaches the tropopause, it is cooled in such a way that it is either forced back into the eye and drops to the warm ocean water that it originated from, or it is caught up in the cyclonic wind currents that surround the eye of the storm, some of which will create the top of that column of very dramatic cloud expression, these cumulonimbus clouds that are so typical of that environment. In a sense, what is being caught up into the upper troposphere in this case, and coming in contact with the tropopause, is being then further incorporated into that very extreme cyclonic wind current that we find throughout that well-developed column. It will, in a sense, or we will witness that the airflow will dramatically increase for this portion of the air that's being uplifted into the developing storm body. And then the last characteristic, and it kind of connects to the previous quality, our sixth characteristic is that these currents force the air out to the edges of the storm where they drop to the ocean or where land surface releases the remainder of the water content. So you can, again, kind of follow these arrows, whether they are moving up to the top of the developed storm engine in terms of the tropopause, or those that are also developing at the edges of the storm body. We will see that uplift. We will see them, again, either go into the eye or move to the edges, and then whatever they're doing in terms of the major division between the air that is being drawn up into this storm engine, they will then drop down. And they'll either drop down on ocean, in the case of the eye, or in the case of some of the airflow that's close to the eye. But then we will also see, as we make landfall and as many of these developed storm bodies push north, if we're looking at those that are associated with the continental United States and the Caribbean Sea and the West Indies, what we'll see then is we will see them being forced back down onto land. And again, the land is cooler than the water, so a lot of the energy that is associated with temperature will begin to dissipate. We'll also see as we move on to land that a lot of the water vapor that these storm bodies are feeding on will also diminish. So with this final characteristic, basically, the air that is being caught up into this major convection storm and storm body is, in a sense, dropping all of its moisture. And then really the entire process begins again if, in this case, there is enough energy and materials to be to sustain the storm body. So if it remains over a warm ocean environment, the hurricane will continue, if not strengthen. As it starts to make landfall, as many of you know, because of that differential, sometimes it will dissipate. So it's a very cyclical kind of process, and it's very systematic in nature. So to summarize our look at this large storm body, let me give you some information, just general information regarding hurricanes in general and the air that is caught up in them. Hurricane airflows are generally considered to be dynamic because they occur both vertically and horizontally in many locations. Don't be misled by this diagram. One of the things that you should keep in mind is that you are looking at a kind of bottom to top or top to bottom cross section of the storm body. Realize also that there is a cyclonic, an additional plane on which cyclonic air and atmospheric moisture are also being moved, and it's surrounding that low pressure environment at the eye. So it has both a vertical and a horizontal quality to this storm. Additionally, the hurricane has extreme pressure gradients outside of the eye. These will intensify its cyclonic wind action until it reaches drier land and cooler land. Air moisture is integral to the workings of a hurricane. The land gives it no renewable resource with regard to that. The last bit of information that I'll provide you with relates to the winds themselves. Hurricane winds are those things that are the most dramatic when we see them on television or when we've experienced them in person. Hurricane winds can reach, in this case, 170 to 190 miles per hour. So they can become pretty significant, and it can cause a significant amount of damage. The winds of a hurricane are weaker at the center. This is the eye of the storm. and on the visual edges of the storm body. However, in between these two locations, so if you move from right to left or left to right across this diagram, as you move from the edge toward the eye, you will see an intensification of the wind speeds themselves, at least those that are below or just within the base of the cloud column. Then as you just about approach the eye, these winds become most extreme. And again, the highest on record that we have right now is about 190 miles per hour. But then you hit the eye where they literally will die off. These extreme winds and the air currents and ocean currents above and below them make the prediction of these storms a nearly impossible task. However, when we get to that kind of third part of our recipe, when we're initially taking a look at the low pressure cell and its development, once it is kind of finally realizing its overall shape, and we start to see those cyclonic systems of air flow around it, we can start to get a sense of the number of paths that it can potentially take. Then in some of these other models, we can simulate changes in ocean temperature and, of course, the air just above it, and then of course we can take a look at changes in temperature and moisture associated with landfall. So these are all then factored in as, in this case, hurricane models are determined. Meteorologists can describe and recognize situations that are conducive to the formation of a hurricane. However, they really cannot for certain say that a hurricane will form, and they cannot for certain determine its overall path. So usually you will see several paths that will be, in a sense, mapped out on television or in the newspaper. They will also generally talk about a range of dates that hurricanes will potentially develop during the hurricane season. Historic trends are also very, very helpful. We have seen hurricane activity increase over the last half century. The most violent and hazardous have been located in the last 30 to 40 years. Patterns of those storm activities over a decade to decade kind of time period also help in the prediction of these storms, when they might occur and to what degree their expression would be. With changes in technology and, of course, changes with regard to how we can track these storms over a decade to decade kind of time period, the accuracy for predicting these storms, and similar to what we have seen with tornadoes inland and definitely in North America, will become more and more accurate. One of the final ideas to take away from this lecture series is that the storms that we've been looking at, and we've been looking at a lot of extreme expressions of these storms, are very much tied to how the atmosphere has changed since the end of the Ice Age. Today, meteorologists, climatologists, geomorphologists, physical geographers all seem to agree on the concept that since the end of the Ice Age, we have seen an increase in storm activities. And to a lesser extent, we have seen an increase in their volatility. In the last 500 years, with the amount of change that has been connected to human activity, you think about the greenhouse effect in general, and many of the greenhouse gases that are associated with that phenomenon, some of which is natural in nature, but other aspects which are cultural in nature as well. We have seen a corresponding increase in the volatility of these storms and in the frequency of these storms.